I was going to have to tell terrible jokes. All right. So, hi everyone, I'm Fallon. As Josh mentioned, I'm working on his team on machine learning infrastructure. And I'm here to tell you about Featran, which is a type-safe and generic feature transformation library. It's mostly going to be a discussion of the motivations for it, how we designed and built it, and a little bit under the hood of how it works. After me, Sammy Hansen is going to talk about how this library actually gets used by machine learning engineers. So look forward to her talk. Cool. So let's begin. I think it's probably good to start with what feature engineering is. Some of you know, and some of you probably aren't that familiar with it. Basically, the definition is it's the process of using domain knowledge to transfer features into a form useful in machine learning algorithms. So this definition tends to just raise more questions, like what is a feature? What does useful mean in machine learning algorithms? So let's start with what we mean by features. Feature is any measurable property or characteristic of a phenomenon being observed. So to make it concrete, at Spotify, we serve songs. So one of the things that we want to learn a lot about and want to use in our recommendation algorithms and other machine learning algorithms is song features. So a feature could be something like the name of the song, maybe, or the genre, or the number of times it got played. So as you can see, I've defined some code here, a case class for song. We'll probably be referring back to this song throughout the slides. And I created a data set called songs. It's just a sequence of songs. And we'll be referring back to that as well. So hopefully that makes concrete what a feature is. It could. Okay, so what does it mean to have a feature that's useful for machine learning? Well, generally machine learning algorithms operate on collections of numbers, so these are usually doubles or floats. For instance, in our recommendation systems, we tend to use some form of collaborative filtering. You create a 2D array of doubles representing users by mapping information about songs or crossing users, your set of users, and your set of songs, and then mapping those to zeros and ones based on whether or not the user liked the song. And then from there, you apply some matrix factorization and some other algorithms to pull out vectors of numbers representing user taste and just representing songs. And then from there, you can use your user vectors in your machine learning algorithms to to make recommendations. So you can check if the user's taste is similar to another user's, and you can do many other things. Probably botched this explanation. I think there's some mixtape engineers in here, so you can correct me. But yeah, so the main point is that features useful for machine learning generally look like a collection of numbers. Raw features that we get day to day generally look like records with multiple fields in them that aren't necessarily something you can easily process. So the question is, how do we get from raw features like song to machine learning algorithm-friendly features like song vectors? And the answer is feature transformation. So to make that concrete, I'm going to walk through 3 basic feature transformations and try to pull out what makes them similar. So the ones I'm going to talk about are the binarizer, min-max scaler, and Hot Encoding. Okay, to start with, binarizer. It's a pretty simple concept. Given a feature and a threshold, return 1 or 0 based on whether or not the value in that feature crosses the threshold. Here's some code to make it concrete. So let's say we're looking at whether or not songs are popular. So we're going to check to see, and we're going to define popularity as having more than 50 million plays. So that's your threshold. So we take our list of songs and we map them to 1 if the number of plays is more than the threshold, and 0 otherwise. And as you can see, that's what you get. So that's a binarizer, pretty simple. Okay. The next one, another basic transformer, is called the min-max scaler. Basically, you give it a min and a max, so you define a range, and then you scale your features to fit within that range. There are many ways to do it, but generally you have to at least find the minimum and maximum of your feature values. So, and then combine that with the min and max in the range that you were providing. So, in order to implement this one, you could actually do it in one pax to get the min and the max. You can take your songs, pull out the number of plays, map those to tuples of number of plays, and then on one side of the tuple, and then do a reduce. And on one side of the tuple, find the minimum, and on the other side of the tuple, find a max. And that way, at the end, you should get the minimum and the maximum. So, and then from there, you can take the min-max that you found and scale your features down to that range. So, as you can see in this last line of code, we're taking X, which is a song, and scaling the number of plays to a range between 1 and 10, and they all here fall between 1 and 10. So that's min-max scalar, also pretty simple. Just take note of the map and the reduce in the aggregation step. Okay, the last one I talk about is called a one-hot encoding. This one is if you have categories that describe features and you have organized them in a sequence, you can transform features into a sequence of equal length with 1 in the position matching its category and 0 otherwise. So this it's kind of a confusing definition, but it's pretty easy to understand if you look at an example. So, for instance, we have this song called Bleed by Meshuggah. Its genre is metal, and we have a sequence of genres. Let's say it's hip hop, metal, and rock. So your one-hot encoding of this song would be 0, 1, 0, because you have 1 in the first position, 0 indexed, which is corresponding to metal. And this is roughly how you would calculate it. You would first find your unique ordered categories, also known as your genres. So first you extract the genre, then you wrap them in a set, so now you have a map of sets. Then you reduce the sets, and that gives you a set of distinct genres. From there you sort them, and you have your sorted array of genres. You can then do your one-hot encoding by mapping over the songs and for each genre in the list of genres, if the genre matches, then it's 1, otherwise it's 0. So you can see in the output in this comment, you have the one-hot encodings, 0, 0, 1, so that means it's rock, 0, 1, 0, that one is metal, and so on. Cool. So, are you seeing a pattern? What's been happening in each step is roughly, you extract the feature you're interested in from your records. So, for instance, in one-hot, you've pulled out the genre from the song. Then you've done some kind of aggregation. So, in some kind of global aggregation, sorry. So in one-hot, that's mapping your genre to a set, and then you reduce it using set union to get your unique genres. And then you map that back to a sequence, so that's something you can use to do your one-hot encoding. And then at the end, you can transform your song, your original set of inputs, which are type A here, using the aggregate of type C that you've calculated, and do your encoding. So this is roughly the pattern. The binarizer didn't have the aggregation, but otherwise you can see this also works for min-max scaling. And so actually those last two steps, the aggregate and the transform, are called a transformer. So I guess now we've set up what feature engineering is, what feature transformation generally looks like, and what feature transformers are. So now we can finally talk about Featran, which is a play on the words feature transformer, but also a really old scientific computing language. So the other name for this library is F77. This was written originally by Neville and Rich Whitcomb, actually mainly by Rich, and they collaborated to make it into the really extensible and nice library it is today. Okay. So we talked about what transformation looks like, and so now we need a nice way to specify it and organize it, because what I showed you in the slides was kind of a mess, like a bunch of maps and reduces, and pretty soon, if you're building a feature that combines all of those things, you're gonna find that your code is getting pretty unreadable. It'll be hard to reproduce, it'll be hard to hand to other people to use. So you want a nice way to specify what it is, and Featran gives you that by providing something called a class called FeatureSpec, and it stands for feature specification. The two methods you're probably concerned with right now are required and optional. They pretty much do the same thing, except, and so I'm just going to talk about required first. You can see it takes two arguments. One is the function that extracts your feature of type A from your record of type T. And then the other argument is the transformer you're interested in. We'll get to the transformers later, but we just covered basically what they're going to be, the binarizer and the min-max scalar and things like that. Optional is pretty much the same thing as required, except that the extraction maps to an option of your feature and defaults to none. Cool. So now you can specify your features. How do you actually do that? It looks like this. You specify your feature spec, you tell it what type of record you're using, then you start talking about, so a feature spec will build up one feature. So in this entire piece of code, you are specifying one collection of these transformations. So the binarizer from before, the min-max scalar, and the one hot encoder, you can see for the binarizer, we're pulling out the number of plays, defining it as is popular, and setting the threshold as 50 million. Similarly for the min-max scalar, we're naming it numPlay normalized, and pulling out the number of plays for it to scale. It has a default min and max, and that's why it's not specified. And one hot encoding for genre, as mentioned. Cool, so now you have your specification. What do you do next? Well, now you want to extract your features. What you do is you call extract on your feature spec and you pass it your input set. So remember that I had a sequence of songs at the beginning, and I can just pass that in without really making any changes, and that returns FeatureExtractor. And before we go further, I'm going to jump into a little bit about the extract function, because it uses the type class implicit pattern, and to give you a lot of collection types for free. So here's the trait collection type, and basically if your collection is something that's included in Featran and it extends, or it provides these methods, then you can pass that collection type as an input into Featran. So things that you get out of the box with Featran include Scala collections, as well as several distributed collections such as Spark's RDD. Cool. So enough about the input. We can look at what FeatureExtractor actually gives you. And these are the things that you're generally interested in, and one other thing. So the feature names, the feature values, and the feature settings. I'll talk about feature names first, because it's easy. Feature names are what get passed to the transformer at the beginning. So you see here it's called like is popular, numPlay normalized, and genre. And after you're done extracting your songs, and you want to know the feature names, you get a list back of what they are they correspond to the order of the feature values. So we can move on to the part that's a lot more interesting, which is the feature values. And the way to get those is you call feature values, but you can also pass it a type, and you'll get back the type that you specified. So a sequence of doubles, if you ask for a sequence of doubles, you can pass in arrays and many others. And another look under the hood, how is this done? Another type class implicit. This time extending the trait feature builder, and this one gives you these sort of generic methods on a one-dimensional collection type. You want to initialize it by telling it how big your feature is going to be, and then you can do things. You can add values to the feature. You can skip values if you don't need them, and you can get your feature result back. And you can also transform one feature builder to another. And if you provide those things, then those are valid output types in Featran. And so Featran provides these out-of-the-box traversable, sparse vector, TensorFlow example protobuf, and many more. You can check out the GitHub if you want to see them. Okay, so that was feature values. And the last one that's pretty interesting is feature settings. So you remember that we covered an aggregator stage. In the original example for Hot, that was your set of genres. And the truth is, like, sometimes you can save those results and not have to recompute them. And Featran provides a way of doing that called feature settings. So once you've extracted you've gotten your feature extractor, you can call feature settings, and it will return a list or a sequence of string. And those strings are actually JSON strings. And they contain things like what transformer it was, and also the values produced by the aggregators. So like I mentioned, in the binarizer, there wasn't any aggregation, so there's nothing here. In the min-max scalar, you actually have stored the minimum number of plays and the maximum number of plays. And for Hot Encoding, you've stored the genre labels, or the unique list of labels. So that's how you use, and then from there you can save this as a file and do whatever you want with it. Because the other thing you can do is you can load it later. Now that you can call the function extract with settings instead of extract, and extract your input set of songs and pass in your settings. And get your feature extractor back, and you can go on your merry way and keep working with it. So those are the three major features of feature extraction: the name, the values, and the feature settings. There are also a few more I can talk about. One of them is built in. It's called feature rejection. And basically you can, some of the transformers will define, will catch errors and provide, okay, let me start over. You can get a collection of rejected features for a record, and based on that, you can choose to keep or reject a record. This is useful because sometimes you just want to know if something went wrong when you were building your feature. Maybe you had an out-of-bound error, or the method didn't work or something. So that's feature rejection. You can use that. You can also combine feature specs. You're basically, these stay in separate, you're building separate features at the same time. Could be useful if you're iterating over the same data set. There's also feature crossing. You can cross the values of a pair of transformers. You just specify the pair, so your binarizer and your min-max maybe, and then you specify a method for combining them. Lastly, there's also a Java API, so if you aren't able to use Scala for some reason, you can do this in Java. And here's a list of transformers that are available. We've got the binarizer, as I mentioned, a bucketizer, hashed and hots, and one hots, heavy hitters, and multiple other scalars. You can check them out. And I guess just to summarize, so why would we use Featran? The main thing is like trying to make reproducibility of feature engineering easier. I'd argue that you get a lot of clarity and flexibility in how you compose and build features from the API. And it gives you the ability to save intermediate stages using feature settings so people can also reuse your work. Also, many common transformers are provided out of the box. And it supports many input collection types and output feature formats. So that's pretty much it. If you want to know more, this is an open source project. Check it out at github.com/Spotify/Featran. Thanks for listening. And do you have any questions? Yeah, it's a supported output format, TensorFlow example protobus, I think. Oh, his question was, you mentioned something about TensorFlow, and yeah, I did, very quickly. It's a supported output format for the features. So you can do some feature transformation and then output it as a TensorFlow example. Yeah. Does that answer your question?
No, I was just wondering so you use TensorFlow as Spotify to
we do use TensorFlow. Yeah. Sorry. Was there more to the question?
No.
Okay. Cool. All right. Okay, the question was, what happens if you load your aggregation and there's something wrong with it? Does the library do anything to detect that?
Or specifically like a one hot encoder if it happens that now that vector needs to grow for a new category.
That's a good question. Actually, I'm not sure. Sammy might know. Sorry to put you on the spot. I don't think it does anything special to check, though. So probably either have wide errors or runtime error.
Yeah, so I'm not sure if you said this, and I didn't quite catch it, but so let's say you kind of scale your original data. Let's say you kind of have a training set and a test set. You then pass it your test set, and it will kind of use the same settings as it did on your training set.
So, sorry, did you repeat it?
Like, let's say you do a min-max scaling, and I want to use the same min-max on my test set as I use on my training set. I don't want to use the min-max from my test set. If that makes sense. So can you kind of store the settings and then apply to the new data set?
Yeah, I think you could.
Thanks for your again.